and mindful in the chat. Do not be insulting, since there can be teacher watching you. So yeah, calm yourself, please. So I think everyone know who is going to be our first speaker, but just as a reminder, as a guest, we're going to have Thomas Cloarec, who you might know by name since he is a former student of our school. He was here last year, and right now he is an engineering student at Centrale Supélec and an AI research student at IRT Saint-Exupéry. For the first conference, he is going to present to you how you can create your own AI agent to play games. So I'm going to show him to you right here. So yeah, welcome Thomas. Wait a minute, I'm just going to put your sound. Yeah, it's all right.
Yeah, welcome. Is my screen working properly?
Yeah, normally everything is working fine, and I'm
Perfect.
going to mute myself and yeah, please have fun.
Yep, thanks. Okay, so welcome everyone. I'm going to present you how to develop your own AI agents, and we're going to use deep reinforcement learning. So as it's told, it's very short. You can ask me questions later during the talk or on my email, which I will show you later. So who am I? I'm currently an engineering student at Centrale Supélec and an AI research student at IRT Saint-Exupéry, where I'm doing reinforcement learning. First, we're going to cover the very basics of reinforcement learning, then the very basics of deep learning, and we're going to combine both of them with deep reinforcement learning. We're then going to see some use cases, so industry and research use cases of deep reinforcement learning, before diving into an example with some code to show you how to develop your own AI agents. So first, reinforcement learning. Reinforcement learning is basically an agent doing actions in an environment and getting observations and rewards. And so with those observations and rewards, you will try to get to better actions in the environment and learn how to have a good behavior. I'm going to show you a really quick example from OpenAI, which is basically hide and seek between agents, so a blue team and a red team. The blue agent try to hide themselves, and the red agent try to find the blue agent. And as you can see, it learns different strategies, so blocking the doors, trying to find stairs in order to enter the shelter. And so this is what you can do, for example, with deep reinforcement learning. To formalize a little bit better the reinforcement learning framework, as I say, there is the agent doing actions at every time steps. So you can see a time step as a frame in the game. So there's an action in an environment, and you get rewards and observation. The observation is designated as a state. So don't be afraid of this formula. This is just going to be some kind of the score for each action. So the Q value will be able to tell you what is the value of an action. And it's going to be the sum of all the rewards the agent will get from a particular action in a particular state. So there is the first reward, the reward of the current state, plus all the future rewards. There is a gamma term right here, squared right here, and it is a float value between 0 and 1. The goal of this value is to say that the short-term rewards, basically, are more important than the long-term rewards, and so we use the gamma term here in order to show that difference. And we can approximate the Q value with just the reward of the next state and the future Q, basically rewards approximated with the Q value of the next state. So this is named the Bellman equation. And at each step t, we're going to take the action with the highest Q value. So this is basically the best action we can take. As you know, the Q value is the sum of the rewards, so it makes sense to take the highest Q value to get the best score. So now we're going to cover a bit of deep learning, the very basics of deep learning. So there is an input layer. You give inputs, so observations, for example, and the neural network extracts patterns from the input and outputs a prediction. For example, you can give it an image. It goes into the neural network, it learns different patterns, and it outputs a label, so basically the prediction of what the neural network thinks the input is. So for example, George. But how do we make the neural network learn? We use a loss function. The loss function is able to compute a distance between the prediction and the reality. The goal is to make the prediction closer to reality, and we use the loss, which we minimize, in order to do so. As you can see, when the prediction minus reality squared goes to 0, the prediction goes to reality. Basically, because prediction minus reality equals 0 is equivalent to prediction equal reality. So yeah, we make the prediction closer to reality. And now, with all of this reinforcement learning and deep learning knowledge, we're going to associate both of them into deep reinforcement learning. And first, with the loss. I showed you that the loss is between the prediction and the reality, basically a measure of the distance between both of them, and we try to minimize it. And here, in reinforcement learning, we try to predict the Q value of each action in each state. So what we do is use the Bellman equation, as I showed you right here, and try to minimize the difference between the prediction you can take here and kind of like the reality we have here. And so it gives this kind of loss, with the goal of improving the Q value prediction. And how do we do it again? We minimize the loss, so the difference between the Q value here and the expected value here. And deep reinforcement learning is kind of like just the reinforcement learning framework, so an agent doing actions in an environment, an observation, basically states, and we feed this observation to the input of a neural network, which allows us to predict the Q value of actions. So this deep neural network is just a function, basically, which allows us to predict something. Here, the Q values, and we take the highest Q value in order to take the best action in the environment. Some use cases of reinforcement learning include very diverse things. So there are games and simulations which use reinforcement learning. For example, Atari, Go, Chess, StarCraft, Dota, Mario, and Lunar Lander, which is going to be shown later during this talk, with a code for all of this. There are recommendation systems that uses reinforcement learning. So for example, Amazon uses recommendation systems with reinforcement learning for their product recommendation. Spotify uses it for music recommendation, Criteo for ads recommendations, and basically it can be used for a whole lot of recommendation systems. It can also be used in robotics, so for example, robotic manipulation, autonomous driving, for example, AWS Deep Racer, and some other applications of robotics. There is also a lot more applications, for example, with Google, who is using data center cooling algorithm, which is made using reinforcement learning. And we can also use it for economics, trading, finance, and a whole lot of different things. For example, as I said, AlphaGo, which you may have heard, where AlphaGo, deep reinforcement learning system, did beat Lee, which was basically the best player in the world champion of Go. Go, which is kind of like a chess, like a board game. Not close to chess, but what you can see from it is very close in some way. The Lee Sedol was beaten by AlphaGo, which is a computer system with reinforcement learning. This is a video of a Rubik's Cube, which is solved with a robotic end. So it comes from the OpenAI lab for robotics. And the reinforcement learning algorithm learns dexterity, so be able to turn the Rubik's Cube around and solve it. You can also see this video, which shows reinforcement learning, which is basically driving an economy, designing taxes, defining how equality is going to be made in this environment. So this is an environment with plenty of people, and we're having a government which defines taxes in order to improve the productivity and the equality in the environment. So it is another possibility for reinforcement learning, another use case. And now we're going to see Lunar Lander, which is going to be what we will see today. This is a space model which tried to land on the moon without crashing, basically. We have observations, so the position of the space model, the position of the land, and we try to take actions with moving to the left, moving to the right, going up, or rotating the engine. Let's see it together. So here we are in the second part of the talk, which is going to be explaining Lunar Lander v2, which is using DeepQ network. So a DeepQ network is basically a deep neural network with deep learning using Q values, so reinforcement learning. And we're going to see how it is implemented. First, we're going to import a reinforcement learning environment. So Jim is used to do it. It's a library from OpenAI. We're going to import Torch, which is a deep learning library. So it is used to make neural networks. We're going to import Matplotlib, so it's a data plotting library. And the first thing we will do is going to be making the environment. So Lunar Lander, which is a reinforcement learning environment, the one I showed you with the video. So we make it. We see that there are 8 dimensional vector for the observation and a 4-dimensional vector for the action space. So there are 4 actions, going left, going right, going up, and rotating the engine. We define the neural network architecture. So that's just the neural network, basically, if you already saw it one. If not, what you can see from it is that it's a function, so linear functions, basically. We create layers. The input goes into the linear layer, and so the state, for example, it goes from different layers to the output, and at the end, it will output the Q values. So that's just a function, a prediction function. We define some hyperparameters for the algorithm. So buffer size, for example, is going to be how many experiences will the AI agent remember. Because when it learns, it is not only going to learn on the current experience, but also on all the previous experiences, or most of them, possibly. And the buffer size is just going to be how many experiences the agent at the same time is going to learn from. So that's mostly a technical detail. Gamma is the Greek letter I showed you earlier. So that's used in order to say that each next state reward is going to be less important by a factor of 0.99. Tau is mostly a technical detail for updating parameters. The learning rate is how fast will the neural network learn. So the highest it is, the quickest, fastest So a neural network is going to learn, even so it can pose some problems if it is too high. And this also is a technical detail. If you want to use a GPU, you can use device, torch device, and all this line, and it will use a GPU if it is available. So we are going to use this code on Colab, Google Colab, which is basically a platform where you can use free GPUs and use notebooks in order to code your Python code and algorithms for machine learning. After that, we define the agent. So the agent has different properties. It knows the state size of the environment. So basically what's the vector of input of the neural network. What's the number of actions, so the action size. And there is a random seed, which is used in order to not do too many different runs, mostly a technical detail again. We define the Q network. So here it is with the state size and the action size. We define the optimizer, so it will allow us to minimize the loss function. There is also a memory, as I said, with a replay buffer, so it just stores experiences, past experiences of the reinforcement learning agent. There is also a function named step, which allows the agent to interact with the environment, mostly to remember experiences. And we take step every time there is basically a step in the environment. And sometimes we learn from the environment. This function act is to act in the environment. And so what we do is take the observation, the state, use the evaluation of our neural network, and feed it, so put the observation into our neural network so that it will output us some actions, some values for the actions. And so we will take the best action, so the action with the highest reward, with the highest value. So we use NP argmax in order to do so. And there is also a detail here, an important detail, which is that sometimes we will take actions randomly in order to improve the exploration. What I mean by that is if you just use a single policy, so a single way of taking actions, you may find suboptimal solutions. For example, to go from a point A to a point B, there are multiple paths. And sometimes the path you found first is not going to be the best one. So we use exploration and sometimes taking actions randomly in order to find a better path if there exists one. So this part here, random choice, is just to better explore the environment and not to stick with suboptimal policies. The agent is also going to learn, so it takes experiences and it will compute the Q target. So that's exactly the expression I showed you earlier. So Q equal to R plus gamma times Q. So that's the Bellman equation I showed you earlier. And this part is mostly technical detail in case of the episode terminates. So if the episode finishes, we will not count this Q value, but don't worry about it. What is interesting here is this equation, so Q equal R plus gamma times Q, the next Q value. So we do so, and then we compute the loss, and we optimize the loss, so we try to minimize the loss. The replay buffer is just a memory, so we can add from it, we can sample from it, so take experiences from it, and feed them to the agent. And the possibly most interesting part, or maybe the finishing part mostly, is the deep Q network, the training process. And so this is each episode, so for each episode. An episode is like a game, you can say it this way. So for each game, you will basically reset the environment, so start a new game, and for each step, you are going to act in the environment, so the agent take an action, we get the next state, so reward for this action, and if the environment is finished, terminated, the agent learns from this experience, so the state, the action, and the reward, and we continue to the next state. So the agent will get rewards for each action it does. So we aggregate those rewards into the score. And here I will show you when we train our DeepQN function, we can print the score. And so after 100 episodes, 100 games, you can see it did not learn much. But after 1,200, for example, games, we can say it solved the environment. So the average score is very high. You can see it either this way with Matplotlib, where we plotted the score. And so you can see after some time, it learns to get a best score, so the best rewards. And some code here to show a video of an agent. And voila, we are on the agent I showed you earlier. So basically, he's playing, the agent is playing, he learned how to play the games possibly optimally, and now it is able to land on the moon without crashing, just by learning from the neural network and the Q values and the Bellman equation. So here it is, and you can use the same methodology on other kind of environments. So for example, here, I use Lunar Lander, but there are also different environments. So you could use Carpool or other environments, which allows you to use another environment and do the exact same thing. So you can keep the same algorithm, maybe change a bit those parameters, the learning rate mostly, and you will be able to train it and see the video of it working, most probably. So wait a bit, obviously, before the environment is solved, but you can do it this way. And so this is it. With any environment which is presented in a good way, so with actions, rewards, you will be able to train a neural network reinforcement learning agent to solve it. So this is it for this presentation. Thank you for listening. If you have any questions, ask me now or ping me on Discord or at my email. Thanks a lot for listening.
All right, thank you, Tema, for being here for us. We have around 5 minutes if you have any questions. Just let me. All right, this should be it. Seems like people are thanking you very much for this conference. Everyone is really grateful for your intervention.
Yeah, thanks. Thanks for listening. Obviously, if you have questions about the best courses to see after this presentation in order to basically continue to learn about this subject,
So
you can ping me. I will send you. Yeah,
we have a first
tell me.
question. What do you do now at ERP and school?
Yeah, so I will go back to it. Okay, so currently, as I said, I am a student at Central Supélec, so it's an engineering school, and I'm also a near research student at IRT Saint-Exupéry. There, I'm mostly doing reinforcement learning research, so I'm just starting. And the goal of it is to be able to make agents that not only learn one environment, but multiple environments. And if possible, that learns faster. So you learn one environment, and after that, you will learn faster another environment. So this is the goal of my research and the research of my colleagues.
All right, thank you. As a questions for myself, I will ask, are there some resources you will propose to help people that are wanting to learn AI and machine learning?
Yes, yes. There is. I will propose one for deep learning, So this will be probably MIT 6S191. So I'll let you put it in the chat.
Yeah.
MI so this is MIT 6S191. This is a very good resource for deep learning. So it shows you a lot of things, very interesting things with code. And for reinforcement learning, it will be the DeepMind course, which you can find on YouTube. So just type YouTube DeepMind reinforcement learning course, and you will be able to find it.
All right, thank you.
It will probably go more into the theory of it, which is very useful if you want to understand what you're doing deeper than just the code.
All right, thank you. So I think everyone here can now try and learn and train themselves in AI and machine learning. So thank you very much for
Yeah,
being here for us.
yeah. Thank you for having me.
Yeah, no problem. So now I'm going to bet you all to wait until our next conference, which will be about deep learning with a new tool that will be presented by an engineer working at Accenture, but I will present it later. So for now, please just wait for us and wait for a good time. I will come back later.